I'm going to put this in a different color just so we can distinguish between what was done on the video and what is done today. If we are looking at f of t plus delta t, now that doesn't, there's nothing in this that indicates that there's a function and that this is what we're actually working with, but I can tell you that that in fact is the case when I see this work here. This entire piece right here is the input. And this whole problem, it could have been written in this manner. The limit as delta t approaches 0 of f of t plus delta t minus f of t divided by delta t. Now, what is the function f? It's not told. You don't have any way of knowing it, so I will tell you that f of t is t squared minus 5t. Oh, that is a little interesting. That really isn't consistent. Hang on a second. 1 second here. Where did that go now? There we go. Okay. If I am going to insert t plus delta t into this function, where does the t plus delta t go? Yeah, I'll repeat it because it's an important question here. If I'm going to insert t plus delta t into this function, where am I going to place t plus delta t? Because it replaces that t, doesn't it? And so it replaces that one and that one. Now, let's look at what we have when we do that. If I replace this t with t plus delta t, I would get t plus delta t quantity squared. If I replace t with delta t, I'd have minus 5 t plus delta t. Okay? Minus, and this says minus f of t, minus, and this part then is just the f of t. Now what we have here is a preview of what happens in chapter 2 when we get to derivatives. This is describing for us a derivative. This is the process we're going to have to take for it. That's why it's so important now to be able to dissect it and see it exactly as it is. And then what we did was we did some expanding. So if I told you on the video that because your Inspire does not have it won't take a delta t as a variable name. I asked you to replace it with W when you went to the Inspire to test it out. And so here we can put in the delta t. So if I treat this as t plus delta t times t plus delta t using FOIL, we expand it. One of the other things I want to make sure we understand is that when we get down to, let's say, this step right here, what we want to be able to do is use direct substitution. Right now, I cannot directly substitute a 0 in for delta t because it makes the denominator 0. However, if I get down to where the delta t is no longer a problem, then I can use direct substitution as I did from here to here. I just directly put a 0 in for delta t. So what we have then, we want to be able to get rid of everything that does not have a delta t in it. If I can get rid of every term that doesn't have a delta t, I can then factor out a delta t from the remaining terms. And that gives me then the ability to cancel that factor in the denominator. This is not your only chance to see this. We're going to see it over and over again, but I want to make sure I point it out to you today. It's kind of like that free information I give you every now and then. You're not responsible for this today, but you will be very soon. I want you to see it early. Okay, let's continue on. Here is a problem where the first thing, I asked you to use a graph, and actually I need to go back and kind of update my words. In our new operating system, it's just a graph page. So what we could, kind of scratch that out and just say a graph page. Okay. Before we jump to that, let's see if we could do something else with this. And that something else we want to think about is, you recognize these as nice trinomials? I mean, you spend a lot of time in Algebra 1 factoring trinomials. Do you ever wonder why you might need to use that? I know I did when I was back in Algebra 1. So now here's a case. If I can factor these trinomials, and if by chance a factor in the numerator would cancel with the factor in the denominator, then I would be able to rewrite this into a form that is identical except at one spot, one point on the graph. Now, why do I need to do that? Well, let's check and see. Can we use, so let's just write the question, can we use direct substitution? That should always be the first thing we check. If we can use direct substitution, don't work too hard. Just make direct substitution. So let's check it. 2 squared is, minus 4 times 2 is, plus 4 is, I think we get a 0, don't we? Okay. So can we use direct substitution? No. Since that's the case, we're going to have to try something else, and that something else is what I was leading us to before. Nice trinomials. Can we factor those trinomials? So go ahead and put down some binomial factors for them. Okay, I've got them factored in this way. If you, if you get to the point where you get tired of trying to do some factoring, you can always use your Inspire to come up with those. But if you factor these, excuse me just a moment. If we factor these and we see that we have the same factors, an x minus 2 with an x minus 2, that then gives us the same, it's the same function but not quite the same. We're going to see why in just a minute. So now I have the limit as x approaches 2 of x minus 3 divided by x minus 2. Can I now use direct substitution?
No.
Unfortunately, no. Okay? So now we need to know what's actually happening there. So let's take the Inspires. The work I want to see on your papers is exactly what we did, what I did on the screen for you. I want to see that you've tried to factor it. I want to see that you know for certain that it will or will not factor into something that you can cancel a factor and come up with a correct replication of it. So let's open it up. Oh, there we go. Okay, so let's do let's look at, well, I'm going to define mine first, just in case I need to do something more with it later. And I have f1 of x. And I had a fraction, so I'm going to put in a fraction here. I'm going to put, and always put in the original. Don't go for something less than the original problem, because you may have made a mistake, and we don't want to have a mistake on there. So just type it in. And I've got it defined. Okay. I want to, well, I can just insert, so I'm going to go in this one to a control on the document. Those of you with the grade inspires, go home and pick up a graph page. And we know that this means that we've got it defined already, so we can just go through and make sure it's visible there. Now, we might see some asymptotes. At times, all we see maybe is what appears to be a hole in the graph. We're going to see what happens here. And sure enough, it does appear that there is a vertical asymptote. A vertical asymptote is that horizontal line that our values, our inputs get closer and closer to the equation of that vertical asymptote, but will sometimes they cross them. Many times they do not. And so if we're looking at this, it appears that as we come closer and closer to the value 2, the left side of it is going to positive infinity, those output values, and the left side, those output values are going to negative infinity. So I'm going to capture that. Wrong thing there. Let's try that again. Capture, there we go. And I'm going to put that in my notes here. And we can look at that a little closer then. If I take then a line, let's see what color, we'll put it in blue here, and I put a line down through that, I can look at that line, and if I can nudge it over just a little bit here. There we go. And nudge it over just a little bit. It should not touch that. And so there it would look like the vertical asymptote. We're going to talk more about those later on. But vertical asymptotes are indicative of when the denominator is going to go to 0. I said that this function has the same look. It's identical to that. Well, let's take a look and see what that does look like. If it does change it in any way. So I'm going to go back here, and I'm just going to look at f2 of x and put in a fraction. And what was that numerator? X minus 3. Good. And the denominator is x plus 2. And, whoops, what did I do? Yeah. So let's correct that. Oh, thank you, thank you, thank you. I probably ran over, didn't I? Oh, thank you. Got that correct now. And if we press enter, and we get that window active, there we go, press enter. I can't tell the difference between, except that if I go to the line, I don't have any other function, any other line that is active. It says f2 of x. And if I say if I look at f2 of x, I see it has that tab, and if I tab it says f1 of x. It is one and the same. So it is the same thing that we have with or without the factoring. Okay, so when we factor, we're not really changing it. Oftentimes, though, we are removing a discontinuity, and that's the discussion we have in our next section. Okay, one last problem here. Comes from your textbook. We all know that we want to remove all the pollutants around, and that's usually the quest we have. We've got this equation that C equals 25,000 P divided by 100 minus P, where P is between 0 and 100, including 0 but not including P. Why would we have this restriction on that variable P? Take a look at the problem again. What does P represent? Percent, right? P is the percentage. We can include 0. Why can't we include 100? They make it undefined. Okay, so there's some good reasons why. Now, if it makes it undefined by using 100, what does that tell you about the ability to remove 100% of the pollutants? It's impossible. Absolutely, it's impossible. What's going to happen with the cost as you get closer and closer to 100?
When you get expensive.
That is where we get a limit, okay? That's what a limit is all about. We're looking at as the percent approaches 100. Now, what does that little negative sign represent? And you say from the left, you know, it might help us to say from less than 100, which is the left, I know, but, you know, from less than 100. But we can't come up from greater than, because you can't have more than 100% anyway. And so when we ask the questions that we have here, we're actually using a limit. Now, again, math doesn't happen because we study it here and we go out there out in the world and try to find an example that might fit the math we'd study in here. Instead, life happens out there, we bring it into the classroom. We have pollutants. We have something down in the Gulf with the oil spill. We have all kinds of things happening in our world. There's another problem that talks about recycling. Don't communities want you to recycle? Isn't it the green thing to do to recycle? Wouldn't it be wonderful if we had 100% recycling? The problem is that the model that has been set up, now who decides that this is the mathematical model computing the cost? Well, it wasn't me, and it probably wasn't you. It was people who observed the data. Where'd the data come from? Out there. They observed the data, and they realized that if they observe the data, it has a certain shape to it, and that shape can be described by this function. And so using this function, or using the one for the recycling one, they realized, we realized after analyzing it, that it is impossibly expensive to have everyone in the community have 100% recycling, which is kind of a sad thing. Now, what we have to do is change the model. How would we do that? Well, what is involved in the cost? Maybe there's some things we can use different processes for, and that wouldn't have the cost become so expensive. But these are the types of problems we have. And again, we don't create these in here and then go out there and try to force it. We gather the data, analyze it, see a scatter plot, determine what would the model be if we want to estimate and predict from it. And then we come in here and we try to look at the mathematics of it. Okay, well, I just wanted to bring those two to you because they are kind of interesting problems, especially this one. So I'm going to just save that, and I'm going to